Hello, everyone, and welcome to Athens or welcome to PyCon, depending on if you're coming from outside of Athens. Let's hope for many more conferences like this one. Let's see what we're going to talk about today. So a few quick words about me. I'm Antonis. If you want to add me on LinkedIn, feel free to scan this QR code. I'm a software engineer. I'm working currently on a product called async. I'm also the crew captain, and I love coding in Python, although I don't do it as much in my day-to-day life. I love Django, as you will see in the presentation, so this is my framework of choice. And generally, I love working with teams, either automating stuff, helping with DevOps, local development, and all those things. So enough about me, because, that's not very interesting, but what's interesting is what we're going to talk about today. So first of all, we're going to go and talk about some primer, some, more basics, and we're going to talk about concurrency and parallelism. Are there people in the room that are clear on the difference between the two concepts? Slight raise of hands. Great, that's a good thing, because we're going to talk about and explain what this is in a bit. Then we're going to talk about the event loop, which is a very important concept when we're talking about concurrency. Why is concurrency? And then we'll go and see some demos and some code so that we can familiarize ourselves on how we're going to use those concepts inside a Django application. So, concurrency versus parallelism. This is a very common misconception among developers. We see many times people either talking about the one or the other, and not being really sure about it. So we're going to go slowly with a few examples and see what they are. So let's start with concurrency. So I think this was from Wikipedia. I do not remember where I got this quote, because I've used it in the past as well. So in computer science, concurrency is the ability of different parts of units of a program, algorithm, or problem to be executed out of order or in partial order without affecting the final outcome. So what does that mean? This means that we can split our program with smaller chunks, and we can start executing one or the other in a random order, not very random, but in a kind of random order. And then at the end, we should have a result that is correct. While in parallel, this is a type of computation where many calculations and the execution is happening simultaneously. This means that, in every point in time, more than one things are happening. So it's not that we take multiple chunks and then we decide the order of execution, but we take two chunks and we execute them at the same moment. Large problems can be divided in smaller ones that can be easily parallelized, and then this allows us to solve those problems in smaller time. And these concepts might be a bit blurry, but hopefully they will be less blurry as we progress in the presentation. So in order to better understand this, so a quick demo. So this is serial execution. Serial execution means that one thing is happening after the other. So in this example, my hand will be the processor, the CPU, and the ball will be a task. So let's say that I need to work on a task. I can start, throwing the ball, catching it again. So my hand or the CPU is occupied with the ball at all times. And then if I need to, start playing with the next ball, I have to drop the next one, finish what I'm doing, and then, continuing throwing the ball. Hopefully the ball will stay near me and will not go towards the audience, but we'll see how this pans out as we progress. Now, when we talk about parallel execution, this means that I have more than one CPUs and I can, keep doing the same work, but I can do it at the same time. So in this case, I have two balls and two CPU cores, one in its hand, and I can keep working, at the same time. So as you see, nothing interferes between the two problems. I cannot, use the two bolts with one hand, because I need two CPU cores to do the parallel execution. And in this example, you see that we have split the tasks between the two CPU cores, and then I can, execute them simultaneously. And, I put a lot of emphasis in this word because it really matters. Now, when we talk about concurrent execution, in this example, you see that the same task, for example, task 1 and task 3, does not, start and finish and then wait for the others. And maybe you saw in the previous example that my hand, so the CPU, was not occupied at all times with playing with the balls. So this means that, hopefully, if I remember how to juggle, I can use one hand and start, executing those tasks. No, that's... My juggling skills are not as good as my programming skills, hopefully. But the idea is that I can have more than one tasks and then, execute them at the same time, kind of. So I'm occupied with both things. And as one thing is in the air, so it's doing something else, the other task can be in my hand and, I can keep juggling with them. So the idea of concurrency is that when you have tasks that do not necessarily occupy the CPU at all times, to find a way to execute them concurrently, so at the same time. So the question usually that comes to mind is, why not just parallelize stuff? And the answer is not very easy, because, it's not easy to parallelize everything, and then you need multiple executors, so multiple hands. I have two, that's my limit, and maybe your computer has a limited amount of CPU. So parallelizing stuff is not always a possibility. Also, in terms of code, when you parallelize stuff, this means that you need to pose the problem in a way that can be executed, in a way that can be parallelized. But usually the problems that we have are more like serial, so it's not easy to make your code parallel from the get-go. Again, you need multiple CPU cores, again, the hands problem. And the most important thing that I have to share today, and I think it's very important to keep in mind, is that we do not necessarily need to decide to parallelize or make things concurrent, but we have to see how we can make those things happen at the same time. So let's say that we can find applications that do not need to be all the time on the CPU. So in my case, the ball was, flying at some point. So those applications are usually web applications, because when your application, let's say, gets hit by a customer or by a user, then you go to the database and ask for a question. What is the ID of user with this session? This is something that, dispatches some work to be done by another system, by your database. And in between the time that you started the query and the query result is back, your CPU is staying there idle. So if you start thinking about problems in this way with API calls, database calls, or other things that happen on the background, you start seeing that you oftentimes have applications that do not necessarily need to run all the time on the CPU. So in this case, we can find a way, and we'll see how we're going to do this in a bit, to yield control, to give the control, too many steps. We'll fix that. So to yield control to another process, and it can be executed. So let's say that those balls are requests. While a request comes from your customer, you can serve it, then go to the database when you throw it in the air, and then continue with the other, and so on and so forth. And we can find a way, an executor, that can execute all these, micro tasks concurrently at the same time. So an ideal program should all work like this. So in this case, we have two CPU cores, so we can do many things in parallel. In a web application, you can think of unicorn workers in this way. So we have multiple unicorn workers that work in this way. And then each worker can do things concurrently. So hopefully this will work, and your program will look like this. So in this way, I will stop here because it worked up to now, and I will not juggle anymore. That was up to what I had to do up to now. And the idea is we can do multiple things in multiple workers at the same time, concurrently. So this is the ideal setup for a web application, and we will start seeing how we can do that thing, that magical thing where we can do many things at the same time in Python. So how can we create or deploy concurrent applications? In Python, there is a concept called coroutines. So anybody in the room familiar with coroutines? So a few of you, that's good. So coroutines are a computer program components that generalize subroutines for non-preemptive multitasking by allowing execution to be suspended and resumed. So this might be too technical, but let's focus on a few of those words. So first of all, the important part is the last one. We can pause and resume those things when we see fit. And when we see fit when we, for example, go to the database. So I start, executing some code, doing some calculations for the customer that just did a request to my service. Then I go to the database. So I say, okay, I'm done here. You can continue working on something else. And when the results are back, I will continue with my application. Or I do an API request, or I do a background task. It's the same concept again and again. It doesn't really matter what I need to do, but when I yield control to something else to be done in the background or in another system, this is where I yield control, so I stop executing, and when the result is back, I will continue with that. And those things are called coroutines. You can find things like green threads or, anyway, many other concepts in other languages. The second thing that we talked about is the executor. We need something that can juggle those balls, those coroutines, in the same way and hopefully better than I did previously. So this thing is called the event loop. The event loop, and again I'm reading from the definition here, is a programming construct or design pattern that waits for and dispatches events for messages in a program. So the idea is that we need somebody or something that when I say, okay, I need to ask something from another API service, yields control to another coroutine, and when the result is back, can give control back to me so that I can continue executing. So this is done with the event loop, which is practically a loop. So it's something that goes through all the active coroutines at all times, and when things are ready for execution, it gives control back to the correct coroutine to keep running. So let's say that we get a bit away from Python and we start with pseudocode to understand how an event loop works. So let's say that we start from step 1. We say that, okay, we have coroutine 0 and we will start executing. So this runs for a few steps. And then at some point, this coroutine needs to go to the network, to the disk, or somewhere where it can yield control. So the event loop will remove this coroutine from the executor, so it will stop executing. It will be, in a post state, and then it will continue to go into coroutine 1 until it reaches a point where, this coroutine again goes to the database or to the network or completes, and continues doing this again and again and again and again for all active coroutines at this moment. And with coroutines, you can easily map them, while not fully correct, with actual requests that come from your customers. So when those requests come, they start executing with their first chance. When they hit the network or the database or something else, they stop executing, and then the next one goes again and again. And then at some point, this event loop has finished with all the active coroutines. So let's say that it did, 10 coroutines. Now, when it goes to the end, it's going to start checking for results. So it goes and says, okay, did the result from coroutine 0 return? Good, I will continue executing. Did the result from coroutine 1 return? Yes. Continue executing. No. Go to the next one. And then when you reach the end again with checking all the results, you're going to go back in the beginning and keep looping. So it's a very simple loop. Of course, implementations are more fun and exciting than the one I'm describing, but a very, very simplistic way to describe an event loop is that start running everything. When it yields control, go to the next one, and then start checking all the results and give back control. When you finish with that process, go back to step 1. It's that simple. So it's a loop that goes again and again and again and tries to run all those coroutines and get the results. And of course, again, we're still in the more theoretical land here, and we will start delving more and more into actual Python implementations and how Python actually implements all those concepts that we talked about. So in Python, the most important concept when you want to have asynchronous code is a library called asyncio. This library is part of the standard Python library, so you don't have to install something. It's out of the box since Python 3.4. If you try to use it between 3.4 and 3.7, results were not amazing, let's say, because Python was not created as a language with asynchronous concepts at its core. So it was improving and improving and improving. And now, at least in the main of the projects that we have worked and deployed in production, it works amazingly well. But if you give it a try, if you gave it a try between those versions and you're not very happy, give it another try. That's my important suggestion here. The introduction of asyncio has some actual language keywords introduced in the Python syntax. The first one is async, which you can prepend before a function. And in this case, you indicate that this function is ready to be run asynchronously. So it might yield at some point, and it will take back control. And the next one is await. Await is a definition that says, okay, do this API, database call, whatever needs to be done there, and I will wait for it. And when the results are back, I will continue running. So await is the way for us to say that this is the time that the event loop can continue to the next coroutine. And when the results from this function execution are back, I will continue running. And of course, apart from those, the asyncio library, so you can import it from the system library, has a lot of tools and things to help us do those things. The next thing that we need to implement here is asynchronous web servers, because it doesn't really matter if your code is asynchronous if you run it within a synchronous context, because in this way you cannot, utilize all those nice new things. I did not say this before, but in order to use all this new syntax, you have to use it all the way. You cannot say that, okay, I have a synchronous Python function here and asynchronous here, and the one calls the other, because if you start blocking, then you will block all the other coroutines that are executing at this moment. So it's not that I have too many workers. Usually in a context that we're discussing, I do not have many web workers. I have fewer with more concurrents happening into one of them. So if I block for one, I block for every other coroutine that is stacked with the same worker. So in order to have a synchronous application, I need to go from WSGI or WSGI, if that was the correct pronunciation, which is the classical interface for creating web applications in Python, to ASGI, or the asynchronous interface of creating such applications. The second thing that I need to do is that I need to start, utilizing frameworks that are async ready. So you might have heard of things like my mind blocked, but there are many asynchronous frameworks in Python, like Ninja, for example, or many others that escape my mind right now. But the good thing about Django is that even though you might have started using it as a synchronous framework, because all the Django core is written as a synchronous framework in Python, you can start blending synchronous and asynchronous things, because Django wants to go and be fully async. It has started adding a lot of nice tools and utilities so that you can start interchangingly using synchronous and asynchronous code. So let's say that you're in Django, you can define an async function with async def, or an async view if you want to be, to have a controller there. And then you can start utilizing those as long as you use an ASGI web server. So this is the important part. Of course, as I told you, Django was written as a fully synchronous framework. So it's not, it doesn't go all the way. It has many things that still need to be implemented to be fully asynchronous. But for example, views are fully sync and async. So you can define one or the other, and you can have even an application that was, written previously using synchronous code. And you can start slowly introducing asynchronous functions, and they will work, one and the other at the same time. And also it has a variety of decorators, middlewares, and other things that are already async ready. So of course, it's more like a let's see if this works case. So you have to go through your dependencies and the things that you work and see if they are already implemented using asynchronous code. Nothing in life comes for free. Usually things either are expensive or make you a bit more fat. So with Django's case, there are a few caveats that you need to take into account when you start migrating to asynchronous code. So first of all, if you have a lot of back and forths between synchronous and asynchronous code, this means that you have a lot of penalty in terms of time that you get, because it's not very cheap to jump from one context to the other, from asynchronous to synchronous or back. The ORM is not fully asynchronous. You will see some async functions starting with A, the letter A, but even those, they are not fully synchronous if you go very, very deep into the code. So you have some penalty in there, but maybe that penalty is acceptable depending on your case. And especially for middlewares, because they are not all rewritten, you have to make sure that the middleware that you use is compatible already with asynchronous code. So how do you see that? You go to documentation, you check, and then you will see. So where does asynchronous code and using ASCII signs? First of all, static file serving. If you have deployed Django applications in productions, one of the first questions that come to mind is, what the heck do we do with static file serving? How do I serve my JavaScript or CSS files? Oh, I have to create a bucket somewhere and serve it from there, or maybe I have a CDN, or maybe I have another implementation. So there's always a question of how. And then if you go fully asynchronous, then this is very cheap, because asynchronous request serving for static assets is very fast and very easy to work with. You get cheap concurrency, so if you have more users, you don't have to deploy more workers of your unicorn server, or more applications one alongside the other, because if your requests are cheap and they only talk to a database or to an external API or do other asynchronous network stuff, you can easily utilize this time and make your application more efficient without changing anything. You can have better resource usage and allocation, because by making sure that at all times the CPU is occupied, if you remember with the juggling trick, my hands were more occupied when I was juggling more balls than when I was doing one, then you can take more performance out of the same hardware. So that's also a good thing. And as we talked about, Django has a lot of things that help you slowly migrate. So you don't have to, turn a key and then tomorrow your application has to be fully asynchronous. You can start doing this on a case-by-case basis, maybe starting with the views that are more expensive in terms of I/O, network, or database queries. This means that you can do this migration gradually. For example, in a few of our applications, we started deploying them as fully synchronous applications, and then slowly we found the API routes that were more, expensive in terms of network and I/O, and then we start converting those and get, a speed up without doing any significant change there. Of course, nothing is more fun. Maybe juggling is more fun, but demos are always welcome. So for the last few minutes, we're going to see a demo of an application that's a Django application that you can also go to GitHub and check it out, that has these concepts. So let's see what we have here. So here I have a very simple application, which is a single file Django application. I'm using Nano Django, which is a Django wrapper that allows you to create a Django application within a single file. And the only reason I'm doing that is to have everything in one file. It's more like for that case. So here, as you see, I have all my settings here and nothing more important. I have admin, I have conferences and talks. So my application is a way of hosting application conferences and talks. And then in the get conferences, I have a call here that sleeps. This is the same as going to a network call and then come back. So I do not do anything fancy here. I'm just adding an artificial delay here. So what I'm going to do is run this application using Unicorn. Oops. And then I'm going to load test it. So now I'm hitting as much as possible this application. And because I only have, how many? I think 4 Ganicon workers. Let's see. Oops. Yes, this application could do only 15 requests. So let's do no code changes. So what I'm going to do now is switch to an asynchronous web server. So now I'm using Unicorn, which is an ASCII server. I did not do any changes to my project. I do the same load test. And in this case, hopefully this will work even better because all those requests can happen concurrently. So you see, previously I managed to do 15 requests in the same time. Now I did 250. So without changing any code at all, because I'm using Django, I could easily switch to an asynchronous code and then, take advantage of all these things. If you open the project, you will see branches that get you through using asyncio to improve this further, and then to use even Unicorn with fully asynchronous functions that have some speed up to go to another step. So I think we're almost at time. We have around 5 minutes for Q&A from what I see. So I would like to thank you for being part of this talk. If you would like to get in touch, feel free to get here. Feel free to find me on X, on Kalipetis. If you are Greek, we have a podcast called Mikri Kouveda. And if you are here at 6 p.m., we have an amazing announcement about the conference happening next year around Django. That's all I'm going to say now, but maybe that's a good hint of what's going to happen. So this is it. And if you have any questions, I'm happy to take them.